Okay, in this video we're going to talk about the acidity of alcohols and phenols. I think you're going to find most of this information is a review from the acidity and basicity that we studied in the first semester of organic chemistry. All right, so to deprotonate an alcohol, we need a strong base. One common choice is sodium hydride, and when the alcohol is deprotonated, that gives rise to an alkoxide ion. It's very common to also use metallic sodium, potassium, or lithium to deprotonate our alcohol as well. In both cases, hydrogen gas is produced and bubbles out of solution. Now, you may remember from Orgo 1, to qualitatively assess the acidity of a compound, we typically evaluate the stability of the conjugate base. So if I want to know how acidic this compound is, I consider its conjugate base and how well the conjugate base is able to stabilize the negative charge. And the way we did that was with REO, right? So in order, we first considered the atom type. So more electronegative atoms or larger atoms are better at stabilizing the negative charge. The second thing we would look at is resonance. Resonance stabilizes the negative charge. If we have other electronegative atoms in the compound, they can draw electron density away from the negative oxygen, thereby stabilizing it. And then we also consider the orbital type, where negative charges in sp orbitals are more stable than sp2 orbitals, which in turn are more stable than negative charges in sp3 orbitals. So it may be helpful to place the acidity of alcohols in context with some other organic compounds that we've been studying. So if we just use the first one, the atom type, right, if I compare alkanes to amines, alcohols, and halogens with a hydrogen, so things like HCl, HBr, etc., right, based on the atom type, oxygen is about the same size as nitrogen and carbon, so it's better able to stabilize the negative charge than nitrogen or carbon. And so alcohols are more acidic than amines or alkanes. But when I think about the larger halogens, generally size is more important than electronegativity. So as long as the X is something like chlorine or bromine or iodine, right, we know that HCl, HBr, and HI are all strong acids, and so they're stronger than the alcohols. Alcohols tend to have pKa's in the 15 to 18 range. Now, if I'm comparing two alcohols to one another, we don't have to consider all of the parts of ARIO, right? I don't have to worry about the atom type, because if I've got alcohols, the atom carrying the negative charge is always going to be an oxygen. And in the case of alcohols, right, that oxygen is always sp3 hybridized. So kind of these two terms are out. So all we really need to consider are resonance, induction, and it's something that I talk a little bit about in Orgo 1, but not a whole lot, and we're going to revisit it here, and that's solvation effects and how they influence the acidity of alcohols. So first, just an example of resonance. If we compare the acidity of cyclohexanol to phenol, we can see that phenol has a much lower pKa, meaning it's significantly more acidic than cyclohexanol, right? The reason being, when I put the negative charge on the oxygen in cyclohexanol, it is not resonance stabilized. In the case of phenol, it is. I can move that negative charge around the ring, thereby spreading out the negative charge and stabilizing it, which makes phenol significantly more acidic than cyclohexanol because the conjugate base is resonance stabilized. All right, if we consider induction effects, so I have ethanol versus trichloroethanol. You can see the pKa of trichloroethanol is significantly lower than the pKa of ethanol, and that makes sense because trichloroethanol has all these extra electronegative atoms that will help draw electron density away from the oxygen when it has a negative charge, thereby stabilizing it. So induction effects would stabilize the conjugate base of trichloroethanol, making it more acidic than ethanol. Okay, so something we didn't talk a whole lot about in Orgo 1 is solvation effects, right? So the more solvent molecules I can get around the resulting conjugate base, the more stabilized it's going to be. And so when we think about ethanol, and I make its conjugate base, Right, ethanol is not particularly sterically hindered, or the ethoxide ion is what we're really interested in, is not particularly sterically hindered. So we can get lots of water molecules around that to help stabilize it. In the case of the butoxide ion that I would form, that it does have significant steric hindrance, so I can't fit as many water molecules around it, and so it's going to be less stabilized. The conjugate base is going to be less stabilized. So that means that the alcohol itself is going to be less acidic than ethanol that is less sterically hindered. Right, and just to kind of show that what we just talked about in a more a better picture than I was able to draw, right? Because ethanol is less sterically hindered, the resulting ethoxide ion, when I pull off that proton, right, I can get more solvent molecules around it, right? The butoxide ion is more sterically hindered, I can get less solvent molecules around it, so that means that the original ethanol is going to be more acidic than the T-butanol. All right, so let's just look at a couple examples. We want to know which of the following alcohols we would expect to be more acidic. So when I think about the conjugate bases of both of these compounds, when I pull off these hydrogens, right, I think in neither case is resonance going to play a factor. So then I would look at induction effects. Because chlorine is more electronegative than bromine, it's going to be better able to withdraw electron density away from the negative charge, and so this is going to have stronger induction effects, and so it will be more acidic. Okay, in this case, if I consider the conjugate base I'll get by removing the protons, in the first case, right, they both have double bonds, but in the first case, my double bond is too far away, so I don't have any resonance structures, right? To have an allylic lone pair, if I start with the carbon atom just participating in the double bond that's furthest away from my lone pair, I've got to get to the atom with the lone pair in 3 steps, right? It was sort of the 1, 2, 3 rule. 1, 2, 3. I can't get there, so there are no resonance structures to stabilize the negative charge in the first case. In the second case, 1, 2, 3, I can draw a resonance structure. And so if we bring the lone pair down, the pi bond becomes a lone pair. Right, so this conjugate base in the second example is resonance stabilized, and so this compound is more acidic. Okay, one final example. In this case, there are no induction effects. I should look at resonance first. There's no resonance. There's no induction effects. And so the only difference here would be solvation effects. Right? In this case, I have a secondary alcohol. In this case, I have a tertiary alcohol. So this compound is less sterically hindered. So I should be able to get more solvent molecules around the resulting alkoxide ion, thereby stabilizing it. And so I would expect this compound to be more acidic.